These are like toenail clippers, not hand nail.
Yeah, but that's what mine are like. Hi, folks. Are you figuring out the radius and the equation and all that kind of stuff? I mean, you could just figure out the radius, but we might as well say, you know, and center. Once we have all that, we can put it in standard form. So we can do pretty much anything with this. So what's your plan?
Maybe use the distance formula.
Okay. So if we use the distance formula to find the distance between those 2 points, that'll be the diameter, not the radius, but we could divide that by 2, right? Okay, so our distance formula, the square root of the change in x squared plus the change in y squared. Or if you prefer, you might want to start getting used to that. Triangles, the Greek symbol delta for change in, but if you prefer the x2 minus x1 squared plus y2 minus y1 squared, you can do that too. Hopefully you recognize this as essentially another version of Pythagorean theorem, right? Just with the square root moved over. Either way, we've got what change in x, so 5 minus 0 squared plus 5 minus 0. Yeah, 5 minus 0 and 6 minus 5. Okay. 6 minus 5 squared. So square root of 25 plus 1, so square root of 26. So thus our radius is the square root of 26 divided by 2. So, Julie, I think that was a great plan. Anybody have any issues with that plan? All right, so square root of 26 over 2, and what, somewhere around 2.5 ish. Okay, so we can find the radius. What about the center? How do we find the center? This is almost a, did you read the section question? Well, does it seem reasonable that the center has to be between the 5 and the 6? What's halfway between 5 and 6? How about their average? Fair. Does it also make sense that it's got to be between 0 and 5? What's between 0 and 5? Its average. You could get fancy and call this the midpoint formula, because it is, but I think it's better if you just think of it as just average the x's, average the y's, and you have the middle. So that center is going to be what, 2.5, and what, 11 divided by 2 is 5.5. Halfway between the x's, halfway between the y's. If you want a formal formula for it, so x1 plus x2 over 2, y1 plus y2 over 2, which is really unusual. Most formulas that involve, your x2s and y2s, you're almost always subtracting them because you want that difference. You want, like, how far did it go? This is one of the few formulas, one of the only ones I can think of off the top of my head, where you're adding them. So it's good to be careful of that. And that's why I often just say it's the average and the average, because average, we know we add and divide. So that's our center. 2.5, 5.5. Could we write an equation? For Z circle? And if so, what would that circle look like?
Is this the one where it's like the x minus h plus the x minus y one?
Minus h squared.
Squared. I always forget the squared and then I get in trouble.
Where does this formula come from?
The ether. I don't know.
Pythagorean theorem.
But, oh, okay. Yeah.
Yeah, it's literally, that x value, this y value, and that radius value.
It's
This is a
rewritten.
change in x and a change in y, right?
Mm-hmm.
Hence the subtractions. Those squared, their sum has to equal the square of that radius because of Pythagorean theorem. Both of these are the same relationship. They're both Pythagorean theorem. You're taking Math 112, right, Hope?
I wasn't planning on it.
Okay. One of the things I tell Math 112 students about the answer to about 70% of the questions that, at least for me, that I ask students in class is Pythagorean theorem. It governs most of the things in that course. So I always tell them, when in doubt, just say Pythagorean theorem. You'll have a good chance of at least being a little bit right. Every once in a while, somebody takes that like literally, and on the big, like the big long word problems, they'll just write Pythagorean theorem.
Better than nothing, I guess.
I always give them a point.
You
If just
get
for
one.
gumption, you know. Surprisingly, it is really the definition of measure in Euclidean space. So it comes up everywhere. And it helps us, remember those formulas. But yeah, once we, that's our equation in standard form. So x minus our x position squared plus y minus our y position quantity squared is the square of that radius. It's one of the good reasons not to turn that into a decimal approximation, because that's just 26/4 when you square it, right? So that's just nice. And I suppose we could turn that into 13 halves. And we have an equation for our circle in standard form. If you want to turn it into general form, I presume you could FOIL those out, but I'm not sure why anybody would want to do that.
I have a question on the equations of the directrix, I think is how you say that.
Yep.
Because I think it is on question 2, I have y squared equals 16x. And the equation for that would be x equals -4. And I'm curious why it was a negative instead of a positive.
Okay, let me see if I understand you. You said the equation was y squared equals
16x.
16x.
And
Now,
I'm sorry, which section was this on?
that would be 10-1.
Okay, thank you.
For me, I would turn that into x equals 1/16 y squared, just to look at it, because then that's your x equals 1/4 times 4. And that's where the 4 is coming from that you're getting, right?
But why it has a -4?
And it should.
Why would it be a negative?
Because this parabola opens that way, right? That 4, that positive 4, is the distance to the focus of 4. The directrix is that way.
Oh, okay, that
Now,
makes a lot more sense.
It's a raw distance of 4, but that line is the line x equals -4.
Okay, that makes more sense. I was like, why is it negative since 16 is positive? And then I was just confused with these on question 3 and 4. Can I give you the equations and can you explain the directrix, because it just was a little confusing. So the next one is y plus 2 squared equals -12 times x plus 3.
All kinds of fun there.
And then the equation for the directrix was x equals 0.
Of course it would not. We'll have to take this apart first, right?
I can give you my vertex and focus if that helps, so we don't have to.
Well, actually, why don't you tell me what you did first?
I don't know. I don't have my notes. I think I did the vertex first, since it gives you the points there, gives them to you.
Oh, was this -12 times x plus 3 like that?
Yes.
Okay, that's a little bit easier. If not, we have to factor out that -12, and that 3 is going to be ugly. Okay, so that's much nicer.
Yeah.
Okay. I'm still gonna move that over here just because I like the 1/4p.
Mm-hmm.
If not, it's fine. It's just 4p there as opposed to 1/4p there. So either one is fine. It's just a habit, you know.
Yeah.
But you're absolutely right. In that form, in either form, the vertex is sitting right there for us at -3 and -2.
Yes.
So you put your vertex at -1, 2, 3, -1, 2.
And then
Is it opening left and right or up and down?
I think I may have just seen what why it got to 0.
So it's opening left and right because the y is squared, right?
Yeah.
And
it's
because of
just
that negative, it's opening that way. The p there, that's 4 times -3, right?
Mm-hmm.
So that p is a -3. And the negative should make sense there because it's going that way 3 to get to that focus.
Mm-hmm.
So that focus would be at what, -6, -2?
Yes.
But you're right, then back 1, 2, 3 puts the directrix on that axis.
Okay. I see it. I see it now. I understand. I was just kind of like very confused of how it got to that number.
It's just a coincidence that the p and the x are the same.
Mm-hmm.
So the vertex moved you out 3, and then the p moved the directrix back 3, so it landed back on the 0.
Okay. That makes more sense. Thank you.
Sure.
I also have other questions if people don't.
Anybody want to jump in there, or? Sounds like no.
Okay.
Go for it.
10.2 got a little confusing for me on question 9, 12, 13, and 14.
Okay. So one you want to start with, or just 9 to be all orderly?
I guess we'll just start with 9 at the very.
What was 9? I can look it up too if you want. You said 10.
Do you want me? I'm sorry.
Well, I can look it up too, because then I'm going to have to ask you the next one. Sometimes there's little weird things that go on, so I might as well. 9. Oh, and 9 had a lot of little things.
Yeah.
So you were given 16x squared plus 36y squared minus 128x minus 72y minus 284 equals 0.
Mm-hmm.
Of course, this problem could be given to you with any of those on the left or right side. It's been set equal to 0 just kind of by convention of general form. But, you know, if these were all moved around, the process wouldn't change. Fair?
Okay. Yeah.
Now, looking at this, we see it's got both an x squared and a y squared. So that should make us think circle-like things, right?
Yeah.
But the coefficients are different. Because the coefficients are different, that's going to warp our circle, making it an ellipse. Fair?
I mean,
Now, if they were so different that they had different signs, if one was positive and the other one was negative,
mm-hmm.
it wouldn't even, it would warp so much that it wouldn't even be circly. They'd turn away from each other and we get a hyperbola. That would be 10.3. If you guys want to look at 10.3, it's nice, but all it does is do that. It takes that circle and just warps it so much it breaks and faces the other way. And there are a lot of applications in physics for both of these things. So that tells us this is an ellipse. Of course, it also, the fact that it's in 10.2 tells us it's an ellipse. And I think it even says, you know, find the pieces for the ellipse. Yeah. But if it didn't, we'd still know what it was just structurally. We talked on Monday about that standard form. That standard form of an ellipse looks a lot like a circle. It should, because ellipses, well, circles are really just special cases of ellipses. They're ellipses that happen to be perfectly symmetric. And because of that, they've got two different radii. They have a radius in the x direction and a radius in the y direction from that warping. So instead of it being equal to the radius is sort of divided out. Hence the being set equal to 1. It's from dividing out that radius, or what's trying to be the radius. So if we want to know where the center HK is, and if we want to know what those radial lengths are, we're gonna need to build this form. So let's grab our pieces. We've got the 16x squared. I'm gonna move the 128x next to it just to get all the x's in one place. And then the 36y squared minus the 72y, just to get all the y's in one place, and let that be equal to the now positive 284, just to get the constants on the other side. Now we know we have to make these perfect squares, but to have a perfect square, we can't have that lead coefficient there, right? That 16 is not okay for completing the square. So we got to factor it out. So we factor out that 16. 16 times x squared minus, what happens when we divide 128 by 16? What is that? 5, 7. Is that 8? Yeah. And then we can figure out what to add there to make it complete. Here we got to factor out a 36, the same reason. Y squared minus 2y. And then we're going to have to figure out what to add there. And still going to equal 284. You might remember when we were doing parabolas and circles, instead of just factoring out that lead coefficient, we could divide it on both sides, right? You just divide it away. We can't do that here because they don't match. If I divide both sides by 16, I'll get rid of the 16, but then I'll have 36 sixteenths. If I divide both sides by 36, the 36 will go away, but the 16 won't. Fair? So we've got to leave them. But that's okay. What do we have to add to this to complete the square? I presume you're all shouting out an exuberant 16. And then what do we have to add over here to complete the square? An equally exuberant 1. Here's the hard part. What do we have to add on this side to compensate for that 16?
Be 16 times 16.
Yep, because we added 16 times 16. So we got to add to the other side all 16 of those 16s. Very good, Sean. Similarly, we have to add all 36 of the ones we added in the y's. That is super easy to forget. And 16 times 16 is a big number, so it's kind of irritating. It's not horrible, but it's enough, I suppose. But then we'll get a nice 16 times x minus 4 squared plus 6 times y minus 1 squared equals, what is 16 times 16? Is it 256? All right. Plus 36 plus 284 is, I don't know, 6, 1, 9, 7, 1. Is that 576? Cool. 576. Okay, so kind of a big completing the square step there, but hopefully after all the completing the square in chapter 3, reminding you in chapter in 1.2 and a little bit in 10.1, hopefully completing the square is getting to be a little bit more familiar. I say it's one of those tools that don't go away, so this is a good time to get real familiar with it. And we're closer to our form. We have these two perfect squares. Now they have coefficients in front of them, but these have coefficients too. It's just the coefficient is 1 over a squared, right? So we could technically, I'm not going to do it yet, but we could technically take that and say that's x minus 4 squared over 1/16 if we wanted to. Right, because dividing by 1/16 is the same thing as multiplying by 16. That would make a really small and kind of irritating radial length in the x, but we could do it if we wanted to. We're not going to yet, but we could. Because the other big thing that we don't have yet is this 1. That 1 is super important. And we get that 1 off by dividing what's, again, trying to be this thing's radius, but that radius is warped by the 6 and the 16. So it's not a common radius. So we divide it off, and we get 16 times x minus 4 squared over the 576 plus 6 times the y minus 1 squared over 576. That forces that 1 to occur. Now, if we're lucky, the 6 will divide evenly into the 576. It'll just cancel nicely. And if we're lucky, the 16 will do the same thing.
How did you get the 6?
By forgetting a 3. Is that better? Okay, good. Thank you for pointing that out. I square rooted it for no reason, apparently. So that's even harder, though. That's got to have a factor of 36 in it. It doesn't have to, but it would be nice if it did. And that is kind of dividing, isn't it? We're kind of dividing that 16 into the 576, right? So if it doesn't divide at all, and it does a little bit, there'll be some reducing going on there. But if it didn't, you just put it in that denominator and call it your a squared. Even if these were both relatively prime, that would be your form. It's ugly. And, you know, I hate leaving fractions in my fractions, but if we're trying to build a specific form, we gotta pay that price. Does 16 happen to divide evenly into 576? Not too surprising. They're rigging the question a little bit. In practical applications, it's very common for it to not be this pretty. But what is 576 divided by 16?
36.
36. It's even a perfect square. They're going to make you soft. What about, well, I guess that would be the 16 then, huh? Again, not always that pretty. It's not hard to make it pretty. You just figure out what that constant would have to be to make that happen. But do be prepared in practical applications. They are rarely that nice.
That definitely helped.
Cool.
I realized what I was doing wrong.
What was that? What was the part that was getting you?
Oh, part of the completing this square.
Was these?
Putting 16, yeah, putting the, yeah, those numbers.
That is a very, very easy place to get a little, yeah.
Yeah.
Or the radius of the major axis, we'd say is 6, and the radius in the, because it's smaller, the minor axis is 4. So if we wanted to graph that, our center is at 4, 1. Right there, 4, 1. In the X, we'd be going out 6. So that's at 4, 1. So we'd be going out 6 to 10, 1, back 6 to negative 2, 1, and then up 4 to what, 4, 5, and down 4 to 4, negative 3. And our ellipse would live. Very rough drawing of an ellipse, but ellipse. Fair? Now, did you guys read the section on ellipses in your text? Oh, you'll get to it though, right? You know, when you make a circle, if you want to draw one out in the world, you put a nail in and you grab a string, right? That nail is at the center and that string is your radius length. And then you drag that around in a circle and it makes a circle, right? Well, how do you make an ellipse? Well, ellipse, instead of ellipse being defined as everything that is the same distance from a given point, that's a circle, an ellipse has 2 foci, the plural of focus, has 2 foci. And instead of these points on the edge being the same distance from the one center, it's the same distance or the same summed distance from those 2 points. So those 2 distances added together is the same as those 2 distances added together is the same as that distance plus that distance. That distance is the same all the way around. Cool. That's what makes an ellipse an ellipse. So if you ever want to build an ellipse out there in the world, it's very common too, by the way, on fences. You ever notice a fence has that nice arched top on it? You know, that arched top is usually an ellipse. And if you want to build a nice ellipse, you drive a nail in, drive another nail in, and you grab a string at a length of the where that you want the height, and you drag that, you know, string with a, you know, marking pen or whatever, and it makes an ellipse. You just really want that top part of that ellipse, and then you go and you saw that top off, and you have a nice elliptical arch. Very pleasing shape to the eye in general. We talked about parabolas having that nice reflective quality where everything bounces to that focus, right? And that's useful, very useful. Ellipses have a similar reflective quality. Anything bouncing off of one, or anything released from one focus, will hit the edge and bounce to the other focus. Anything released from one focus will bounce off the edge and hit the other focus. And always travel the same distance, no matter what. Because that distance is that common distance that defines the ellipse. So not only will all of those things end up at the other point, but they'll end up at the other point at the same time, if they're released at the same time. Fair? This is used a lot in medical applications. You put somebody's kidney here. I mean, when it's in their body, you position them so their kidney is on one focus, and the other focus has a low frequency sound emitter, and you thrum that emitter, and all the sound energy, all the little vibrations bounce off this big ellipse that's back here. There's no ellipse on this side, there's a person. But all that energy hits that back reflector and strikes that particular location all at the same time. And they position you so that a kidney stone is right there, and that kidney stone will shatter without doing too much damage to the surrounding tissue, so you can pass that kidney stone. Is an example of a place we use ellipses. If you've ever been to a large domed building, particularly the Capitol building in Washington is famous for this, but most domes have it. All domes have it somewhere, but you can't always get to it. But there's often a place under that dome where if you are standing there and somebody else is standing at the right spot, say on the other side, and they're talking, all the sound of them talking gets reflected directly to that location. And because it's all focused there, if they're over here whispering really quietly in a noisy room and you stand in just the right spot, you can still hear them as if you're standing next to them. There's a famous legend that Benjamin Franklin put his desk under the rotund at one of those foci and had them put a bunch of potted plants and stuff over in front of the other one so that people would go behind the plants to have secret conversations, and he'd just sit at his desk and hear everything that they had to say. Benjamin Franklin was known for being both a scientist and a little shady, so I wouldn't be surprised if that's somewhat true. I also wouldn't be surprised if it's not true, but it's fun either way.
Weren't all scientists back then kind of shady?
I like to think so, but he was particularly shady in anyway. Anywho, also one of the other things that we use ellipses for, or need to know about ellipses, is if you're, say, out in the way too colorful universe. I just like that I have a pen that can do that, by the way. It's not necessary, but it sure is fun. If you're out there in the universe and you're some object, large objects in the universe collect things orbiting around them, right? And we often think of orbital paths as being circular, but they're very much not. Orbital paths are elliptical, particularly if you think of things like comets. You know, comets, how they'll go way away from the sun and then they'll come back really fast and then go way away from the sun. Comets have extreme elliptical orbits. Our orbit around our sun is fairly circular, not quite though, but it is fairly circular, as most of the major planets are. But it's not a perfect circle, it is an ellipse. And that source of gravitation, that large object that you're being pulled to, is always on one of the foci of the ellipse for that orbit. The other space, there's nothing. It is just empty space. But the source of gravity is always one of those foci. And you get accelerated toward it. You're wanting to come slam into it because it's pulling you toward it, but you're going too fast. So you curve around. And then you go further away. You slow down a whole bunch, sometimes, depending on what's going on. But then you can't quite get away because you're stuck in the orbit and you get pulled back and you just keep going around on that long elliptical course. Not only does this happen with gravity and planets and so forth, it happens with magnetism as well. It even happens with the strong and weak forces, subatomically. So all primal force attraction follows these elliptical paths. So if you're going into physicsy stuff.
I'm sorry to
What's that?
interrupt, but can we go over 12, 13, and 14?
Yeah. But some of those, I think, talk about those foci, right? I thought they
Yeah.
did. That's why I want to talk about foci for a bit. But so that's why foci are important. It's always good to stop me when I start going on the whole, isn't all this stuff so cool stuff. Oh, they even have a picture. Whisper roots. A's.
I honestly just wanted to see what the answer was because I
Right.
was so confused.
Oh, that's a totally reasonable thing to do. Ew, that's an ugly answer too. Okay, that one doesn't have any foci in it, so we'll get back to foci in a second.
I refreshed it and I have a different question too.
Well, let's do the one that was here. That way you have to do that one still. Is that fair? Sort of. So that's our center, our major axis. The major axis is always the long one. So major axis is 10, and it's passing through some point at 6,1. So first and foremost, I'm going to draw this. So 4, 5. I don't know why I drew it so high. It goes through the point 6,1. So 6,1. So it goes through a point there. And the major axis length is 10. We do have to figure out, well, which one is the major axis, unless it tells us here. Major axis length of 10 passes through the point. Okay, it doesn't tell us where the major, which one the major axis is. Oh, horizontal major axis, okay. So it does say horizontal. I think we could do it without being told that, but it's a lot harder and ambiguous, so. So we're told that's horizontal. So we know our major axis goes out to 14.5. Nope, major axis length is 10. So it goes out to 9.5 and back to -1.5. If the major axis length is 10, then the radius, the axial radius is 5. So 9.5. And we know it goes through that point at 6.1. Okay, not my best diagram ever, but does that translation of that information seem reasonable? Okay. So then what do we know? We know that our form should look like x minus h squared over a squared plus y minus k squared over b squared equals 1, because that's what all ellipses look like. We know that that hk has to be 4 and 5. For the center to be where it is. And we know this radius in the horizontal direction along that major axis is 5, which means that A is 5. Is that fair so far?
Would you mind
Unless-
repeating that? I'm sorry, you cut out.
Sure. We're told that this major axis length, major axial length is 10.
Mhm.
That means that radial length along that axis
Oh,
has
yeah.
to be 5, and that's that A value is then 5. The
Thank you.
Sure. The only value we're not told is that B, right? But we know that we have to pass through the 0.61. That means if we let that X be 6 and the Y be 1, this thing has to be true. Fair? So we could presumably put that 6 and 1 in there and solve for B. We have 6 minus 4 squared over 25 plus 1 minus 5 squared over B squared equals 1. So 2 squared over 25 plus -4 squared over B squared equals 1. So 4/25 plus 16 over B squared is 1. And you could use any set of solving techniques you want, as long as you subtract. 25. That would turn into 25/25. Yeah, sorry. So, and B squared, sorry. So 16 over B squared would then be, what, 29/25. I'd be inclined to just flip those. Just because it makes our lives easier. So B squared would be equal to 25 times 16 over 29. I'm not going to figure out what 25 times 16 is because we're about to take its square root. So that'll be plus or minus 5 times 4 over the square root of 29. So B is equal to 20 square root of 29 over 29. Actually, I'm leave it as 20 over square root of 29. usually we'd want to rationalize that, but we're going to square it in a minute, right? So if we're going to square it, I'm not going to bother rationalizing it just so I can square it. So that means we know what that B is,
How'd you get the 29/25 really quick?
the 29/25.
Oh, wait.
Oh, this one?
Yeah.
Added like terms, or subtracted. That should be 21, shouldn't it? Thank you. Is that better? Thank you for that. So then y minus 5 squared over what's now 400 over 21 equals 1. So it really is just plug in everything we're told and then use the point to solve for whatever else we need. Cool. Oh, I don't know if I told you guys, I figured out why you weren't seeing the test scores. I kept trying to fix it, but I was fixing an old version of the test, not the new test that you guys took. So as soon as I figured that out, I was able to make the other one show. So you should, if you haven't seen it yet, check it out. But I apologize for that. That was just me doing the right thing to the wrong thing. So as we talked about, whisper rooms. Let's see, do we need that there? Yeah. So before we talk about that, we do need to finish the one piece to our discussion here on foci. So let me do that, but then we can answer 13 and possibly 14. Okay.
I do need to leave at 2.
So do it fast.
Yeah.
Okay. The big deal with foci is, remember I talked about that string? We know the length of that string, however long that string might be, because we know that if we're, like, say, pulling the string to this point, it's going to go this way and then back that way. Fair? So the length of the string is going to be this length, but this length twice, so the same as that length. So that string is the length of the entire major axis. Fair? So the string length is twice our A value. In our, that A value at there was 5. So over here, that A value was 5. So anywhere we reflect from a focus somewhere and back, the length of that path has to be that 10. No matter what that path is, it's not starting from the center. That's just what happens when you rush me. Sorry. Whichever path we take, that path length is going to be that 10. Fair? And particularly if we pull that string directly up to the minor vertex, we know this length is B, the length of the minor axis, the B, which is squared there. And these lengths are each A, because they're each half the string. Fair? That means we can find this focal length, which we usually call C, with a particular formula. Hope, what is that formula?
Give me a second. Oh, wait.
The Pythagorean theorem. Sorry.
Pythagorean theorem. It looks a little weird because it's b squared c squared equals a squared. We're used to the labels being different, right? But they're just labels. So that relationship gives us a relationship whenever we need to talk about A, B, and find that focal length or deal with that focal length. That Pythagorean theorem relationship is the relationship that we need to use. Cool. So in your 13, you're given this whisper room. You're told, standing on the other, where are the measurements? Whisper room gallery has a length of 178 meters. So you're told that's 178. And the foci are located 39 meters from the center. So wherever the center is, that's 39 meters to each focus. And we're asked to find the height. Well, that height is our B value, right? Our A value, that A value is half of 178, which is what, 89? So our A value is 89. That makes sense, Julia? But the key is that this A value can actually slide up and is that hypotenuse length, because that's how long the string is. Okay. So then we get that 39, that 89, and that B. That B is the height. And you know that that B squared plus the 39 squared is equal to 89 squared, and you can solve for B. Cool. And once you have that A, B, and you could make an equation, you can do anything you want from there. But we need that Pythagorean theorem relationship for that to work. 14 real quick. In some ways is similar, except there's no, we don't care about the focus here, but we're told we have an elliptical bridge arch. Arches are often elliptical out there in practical applications. That is 110 feet wide. So that's 110. You can probably guess that we're gonna care about that 55 radial length, right? And is 12.4 feet tall. So 12.4 feet tall. What is the horizontal? Is this just the distance from the center of the arch? Oh, sorry, 34.5. 34.5 feet tall. And they want to know how far from the center. So how far can we go from the center so that we're still under a height of 12.4? Presumably so trucks can drive under it, right? Or something like that, or boats can float under it or whatever. Well, notice we're given our B and our A, right? Where's our center? Our center is wherever we want our center to be. So why don't we go ahead and just say it's at the origin. So then we got x squared over 55 squared plus y squared over 34.5 squared equals 1. That's the equation of our bridge arch, as long as we consider that to be the point that is 0, 0. You want to know what those x values are measured from the center when the y value is 12.4. Okay, so then let the y value equal 12.4, and you can solve for x. And it's 2 o'clock. You thought I couldn't do it. That work for you? Okay. Did we talk about meeting tomorrow to answer anything else you guys have? Yeah, okay. Good.
Thank you so much.
No problem.
Okay. Bye.
Bye.
Thank you.
Sure. You guys need anything before you go?
I don't know. Did you upload the Monday class video? I wasn't able to find it.
I'll go check. If it doesn't show up soon, send me a message and I'll find out why that's not showing up.
I'll harass
But-
you.
I work well under harassment. I do.
Awesome. Thank you.
Sure.
Have a good one. See you tomorrow.